Okay, good morning, everyone. I think this is where we were. We had pretty much finished talking about the various properties of light that we're going to need in our understanding of quantum theory, except for this last one, which maybe is the most obvious and the simplest on one level, is that heat does create light. And the hotter something gets, we've noticed that it actually changes color. We have the expression of red hot, yellow hot, and even white hot. What's going on with white hot, of course, is we know that white light, sunlight, is a combination of all the colors. What's going on as the material, the solid materials are getting hotter and hotter, the spectrum of light that's being given out, and I remind you one more time that when light is being given out by a natural phenomenon, it is not being given out at just one wavelength, at just one color. It is always being given out in some kind of a spread of colors, like something like a graph like this. Here, the frequency is being measured here on the x-axis. We just as well could have had the wavelengths down here because we know they're equivalent inversely in terms of their sizes, but equivalent because they must multiply up to the speed of light. So here is the intensity, the brightness of the light, and the brightness of the light does change with the different colors depending upon the temperatures. So here's a relatively cool temperature. The temperature is getting hotter and hotter and hotter, and the spectrum that's being given off is changing in two ways. One is the overall amount of energy that's being given off is getting larger and larger. That's what literally the area under these mountains are computing. For any of you people who remember your calculus, this is an integration of the curve, which will give the total area under the curve. The other thing, just as significant, is that this peak, notice, is going to higher and higher, higher and higher frequencies, and therefore shorter and shorter wavelengths. And so for something which is white hot here, okay, all of the colors are being given off, not just the red, but the yellow, the green, the blue, the violet, all the colors are being given off, even some ultraviolet, at this very hot temperature. And what do we see when all the colors meet our eye at the same time? We see a color that we call white, okay? Like the sunlight. This phenomenon was of great interest to the physicists at the end of the 19th century. We're trying to figure out these kinds of curves. Here they are again, looking at different temperatures getting hotter and hotter. Notice two things, that the amount of energy being given off is getting greater and greater as the overall mountains are getting bigger and bigger, and the peak wavelength, here we are talking about wavelength, the peak wavelength is getting shorter and shorter and shorter, okay, as it gets hotter and hotter. This yellow line here is the spectrum of the sun, which we've noted already peaks in the visible, but there is ultraviolet light and infrared light in the spectrum of the sun. The corona of the sun is about 6,000 degrees, a little bit less than 6,000 degrees. So physicists were trying to understand these curves. Why? Why was this? Well, of course, it's an interesting phenomenon in itself, but if you think about it, what's happening here is that heat is giving off light. Now, classical physics has two great pillars. One is the Newtonian paradigm of forces and accelerations and motions. And part of that great synthesis is the understanding of heat as the motion of molecules, as the motion of ultimately of atoms. So the idea of heat, thermodynamics, and all of the properties of heat were subsumed under that Newtonian paradigm of motion. On the other hand, the other pillar of classical physics is electricity and magnetism. And the great synthesis there of bringing light underneath that paradigm. Just as heat was brought under the Newtonian paradigm, light was brought under the Maxonian paradigm of electricity and magnetism, where the equations of Maxwell literally predict an electromagnetic wave, which has the speed of light, and nothing has the speed of light except for light, of course, electromagnetic radiation. And so light must be an example of electromagnetic radiation predicted by Maxwell's equations. So this is the great synthesis of classical physics. And what are we looking at here? We're looking at a phenomenon that has both. The heat is creating the light. If this could be understood, maybe we have a grand synthesis of both paradigms being explained by one coherent set of ideas, ultimately one theory, one set of grand formulas. Very similar to the goal we still have today, right? Looking for the theory of everything, trying to merge up the theory of quantum theory and general relativity, where everything could be explained in one way. Same thing here, but just more modestly, because we have the simpler classical physics to try to measure up. So this was a big deal. This was something that if it could be done, you would go down in the history books like a Newton, like a Maxwell. Okay. This is before the time of Nobel Prizes, but this is, you're talking about immortality, certainly. The people who got this ball rolling in terms of studying this is two people of the 19th century, Kirchhoff and Bunsen, of famous Bunsen-Bern flame. And here's the spectra that they studied. Here again is the spectra here of 6,000 degrees, 5,000 degrees. Somewhere in the middle here is the spectra of the sun, peaking in the visible light. And this is called black body spectrum because the materials that were giving off the light that they were studying, they wanted to have the property that it reflected no light. The only light coming from these bodies was what was being generated by its heat. They were looking for a pure and as physical model as they could to study the theoretical curves. That's where the strange expression of black body comes from. It's a body which is only giving off light, it is not reflecting light. And a good example of that would be a star, the sun. The sun does not reflect light, okay? It only gives off light due to its temperature. The other key element of a black body radiation is the spectrum that it is giving off in its various wavelengths only depends upon the temperature, doesn't depend upon its chemical composition. Okay, so you can focus just on the parameter of temperature with the various different wavelengths at the different brightnesses. You didn't have to worry about the chemistry of what was going on. The other great advantage of a black body. So that's where this strange word comes from. The idea it doesn't reflect light and therefore would be in that sense a black body, kind of like a black hole kind of thing. No light, can be reflected from it. All right. Another example where the stars are a very good black body. Here is one more picture of the sun peaking here at the visible range. Here is a cooler star, Antares, which is, as you may remember from your astronomy, is a red giant. And here is a very, very hot star, Spica. And, in our beautiful light skies, dark skies, you can see when you look at the stars. Some of the stars, are white. Of course, most stars are white. Some stars do have a reddish glow, like Antares. It does have a reddish kind of yellowish kind of color to it. If you look at a very, very hot star like Spica, a very, very bright star, the brightest star, Sirius, is also a very, very hot star. And it's very, very bright. Spica is as well. And I think you'll agree, if you look at that star on a really dark night, it has a cold whiteness to it, almost what you'd call a blue kind of white. You're not being deceived by that, because the visible light of that star actually peaks in the blue and in the violet. Okay, there's plenty of red and orange light in the light, so that it does come out to us as white. But it actually peaks in that blue range of the visible. In fact, it actually peaks in the ultraviolet range as an overall peak, but the brightest visible light that you're looking at in Spica is actually in the blue. And so it has that bluish kind of overall tint. So this is the phenomenon that we're talking about. I try to point these things out you know, with the uh, interference patterns of the oil slicks to try to make this is not just stuff going on in the lab, okay, that physicists work with. These are things that we see in nature if we know how to interpret them. Okay, so what was the goal? The goal was to try to find a theory, an equation, if you like, mathematical model that could predict those curves. They are curves, they have a graph. There's an X and a Y axis. You should be able to find a formula that'll predict Y, which is the brightness of the light, given the different wavelengths. And you'll be able to plot points. If you hold the temperature constant, you'll get a graph for a certain temperature. Well, one of the first successes was our friend Wien, remember, of the cathode rays going the other way, the so-called canal rays, who he first discovered and studied. He made a great contribution in this study of black body radiation by finding a formula that would show where the mountain would peak. What was the brightest wavelength that would come out for a given temperature? Very nice, simple formula right here. The temperature times that maximum wavelength will equal 0.0029, where this is measured in Kelvin, of course, and the wavelength is measured in meters. Okay. This is a very, very nice formula. It kind of gets us along the way of what's an important characteristic of our graph. A little bit of fun with it. If we take us, 100 degrees Fahrenheit, 330 degrees Kelvin, and you use Wien's formula, you'll find that we radiate, our highest radiation is in the infrared. And so we have the infrared cameras so well used by the spies and the good guys and the bad guys of seeing things in the dark, because we do glow. And here's the hottest part, looking at the skin. Here, this cooler, because the radiation from the skin has got to get through the man's shirt. And here is the coolest place of all on him is his sunglasses, his glasses, where the light from his skin at that point is being blocked almost entirely. And so it is quite cool. The other fun one could be the sun itself. We know that the sun peaks at 520 nanometers in the yellow-green range, and from that you can calculate the temperature. What must the temperature be? Putting in that maximum wavelength that can be put into the formula, and we could solve for the temperature. Algebra goes any way you like. You can go ahead and solve the temperature, knowing the yellow-green maximum thing, and find the temperature of the sun. And this is how we know what the temperature of the sun is, by using Wien's formula. Okay, so, but it is Max Planck who actually solves the problem. And this is his equation, okay, which describes mathematically all these graphs. Now, it's a bear, it's a monster. We're not going to work with it in any way, but just look at it for a second. If we hold the temperature constant, okay, let's take it at 6,000 degrees. Don't change T, but put in a bunch of different frequencies. I apologize for the Greek letter nu. I don't know why authors continue to want to use the Greek letter nu. It looks just like a V, which of course we use for velocity, but this, as we know, scientists say they love their traditions, and this is very much still a traditional letter that's used for frequency. I will use F. I see more and more authors are using F for frequency. Some people don't like to use F because F is the universal letter that's used for a function, and all of these things are functions. So anyway, that's what this is. This is simply the frequency. So if you want to know what, holding the temperature constant, if you want to know for a given frequency what the brightness is, this is how you will calculate it. Okay? You will need to put the temperature in the formula, and here is the two places where you put in the frequency. You put the frequency in the numerator, cubed, and you put the frequency down here, raised to the exponent of E, one of the great constants of mathematics. And so these are the two variables. Everything else here is a constant. Here's Planck's constant, speed of light. Planck's constant again appears. Of course, 2 and E and 1 are themselves constant, and this is Boltzmann's constant. Very interesting. Yeah. Boltzmann's constant comes from the paradigm of heat and thermodynamics. C comes from the paradigm of electromagnetism. This is the inherent speed of all electromagnetic waves, according to Maxwell's theory. And here is what we'll become to call Planck's constant. All these three major constants, H, C, and K, you're looking at the synthesis of the two great classical paradigms of Newton and Maxwell combined in this formula. It is a great triumph. Okay? Story goes, when he actually released this formula in December of 1900, and that's the traditional birth date of quantum theory, we'll get to that in a moment. He gave this formula at a talk at the Physical Society in the evening of December of the end of the year 1900, and he releases this formula describing these curves. Just so happens that at that same conference, at that same meeting, some physicists, experimental physicists, had come with new data for black body radiation. Brand new, off the presses, best equipment, best measurements so far. And the room was blown away because this formula that Planck unveiled that night described their data perfectly. It was just flabbergasting. So everyone wanted to know, Max, where does this formula come from? How did you derive, what are the ideas behind this formula? Because it is indisputable. It describes the data. It describes these curves. Okay, so if you were to take a temperature of 600 and hold T at 600 here and put in a whole bunch of frequencies and just keep computing the brightnesses, you will get all these different points. They will all line exactly up. Different frequencies will give you different brightnesses doing this bunch of arithmetic. Where did this formula come from? Well, that's a good question Planck would have asked. The phrase that he used later in life in describing the processes, it was a moment of desperation. It was an act of desperation. He literally says this in trying to understand what was in front of him. Now, it may strike you guys strange that how do you come up with a formula, specifically like that, and not kind of like have a theory? You're still desperately thrashing around for the underlying ideas. This is because Planck is an expert in this area. He's worked his whole life, his whole professional life. He knows these kinds of formulas. Okay, the formula here that we were looking at, this formula here, we could show this to someone who works in thermodynamics, who works in the distribution of the different kinetic energies of the molecules of a hot gas. There's great similarity in this kind of formula with that kind of formula, the distribution of temperatures. Okay, this does not come out of no. This is not someone's dream or nightmare. Okay, he knows how to fool with these kinds of variables and where they go and what to use to get the kind of curves that you're looking at here. What's incredible is the introduction, of course, of this, of Planck's constant. This is something new that you won't find in any of the formulas for the two classical paradigms. This is his desperation of putting this in. Okay? Now, we can't describe the mathematics of what's going on. We can't go into that formula in any detail, so we'll have to do it in words, explain in words what it is that was in Planck's mind to derive finally that formula. That'll have to be good enough for us. And so his assumptions were that the electromagnetic energy being produced by the black body, the atoms that were comprising the black body, come in discrete individual chunks, or what he called quanta. The amount of energy associated with the smallest amount of quanta is dependent upon the frequency of the light. It's in fact proportional to the light. So for any particular frequency, the energy is some constant times that frequency. That's how you take a proportion and turn it into an equation, by having a constant of proportionality. That constant we now universally call the letter is used as H and is universally called Planck's constant. And so here is the formula. that the energy for any frequency comes in these chunks, proportional to the frequency. And here's the amazing thing. It can only radiate in discrete amounts of these chunks, where n is 1, 2, 3, 4. This is the revolution of quantum theory. This is the beginning. You don't have whole numbers, guys, in physics. You just don't have whole numbers in physics. But here is at the very foundation of what he is looking at, his energy of all things, which is a continuous quantity, 1/2 mv squared, where m can be anything and v can be anything, and so the energy can be anything. Planck is saying no, it can't be any. It can only come in these discrete pieces. For a particular frequency of light, it has to come as h times f, and not just only h times f. It can come as 2h times f or 3h, but nothing in between. This is his act of desperation. Okay? He didn't know what to make of it. No one else knew what to make of it. He was very unhappy with it. He tried for 10 years to find some other way around this basic assumption to derive his formula without success. The first person who takes this formula and actually runs with this idea of chunks of energy of light, who runs with this idea, who uses it in some kind of way, is Albert Einstein. And he uses it to explain another phenomenon that was greatly studied at the end of the 19th century, the so-called photoelectric effect. There was almost just as much energy going into trying to understand this as for the black body radiation. And here's the setup. We're again looking at a cathode ray tube. Yeah, looking at that Crookes tube again that we see over and over again. We have an evacuated tube, which is hooked up with a negative and a positive plate, cathode and the anode. We set a small voltage in between, not high enough to draw the cathode rays, as in Thomson's tube, but just a small little voltage, so that if there were any free electrons in here, they would drift over from the negative to the positive plate, and they would be registered in an ammeter as a current. But just turning this thing on, just turning on the very low battery juice, you would get nothing, because the voltage is not high enough to tear any electrons away from the cathode. The cathode is not hot, as in Thomson's tube. That's literally boiling off electrons. It's kind of an inert thing. Until you shine the light, this simple ordinary light, on the cathode, on the negatively charged plate. You shine light on the plate, and all of a sudden you get a current. The electrons appear. From where? Well, they must appear from the negative plate. That's where you're shining the light, after all. The light must be releasing electrons, just as the heat was releasing electrons in J.J. Thomson's experiment to prove that there were electrons in the first place. We just have another source of energy, light energy, which is freeing up the electrons from the metal plate, just as, for example, Röntgen was using by having his electrons knock into a physical metal plate, giving off light, giving off X-rays. So it's not surprising that you put energy in, you're going to get energy out. That wasn't surprising. We know that we could have brought a radioactivity element close to this piece of glass, and it would have created a current, because the uranic rays, the alpha particles, the beta particles going into the glass would excite the air, in this case, a little bit of air that was left in the tube, and it would free up electrons, which would show up. So this is not a surprising thing. Okay? This is nothing new here yet. But what was found was that for any frequency of light that you wanted to use, some frequencies worked and some frequencies didn't. It didn't matter how bright the light was. If you used a red light or an orange light, you got nothing. You could have the brightest red light you could possibly, it would burn your skin. It would burn your eyes out, this red light. It would do nothing to create a current here. You shine a little itty bitty violet light, and all of a sudden you get a current. This makes no sense classically, because the energy of the light is in the brightness. The energy of the wave is in the amplitude. The energy of the water wave is in its how high the crests are. The energy of the light wave is in the amplitude, which is the brightness. The color of the light is the frequency and the wavelength, not the brightness. This is what was so fascinating to classical physicists, that this was not behaving the way it was supposed to be. Energy was not behaving the way it was supposed to be. Yeah, just like the black body radiation, huh? Yeah, the plot begins to thicken, right? Okay. Of course, if you did have the right color of light, finally, and you did increase the brightness, then the current would increase, okay? If you had more light of the right frequency, yeah, you would get more free electrons. Okay, so let's just quickly go through, in summary, what the classical interpretation would expect of a setup like this. Since light's a wave, the energy is delivered to the surface proportional to the intensity of the light, the brightness of the light, the brightness of the light. Since the energy of light is spread uniformly over the surface, because it's a wave, it's transferred continuously to the electrons in the metal, and this will just have to build up until finally the energy of the electrons is high enough to free itself from the metal. Right? The metal is holding on to its electrons in some way. You have to give it finally enough energy so it'll be freed up. Very much like putting heat underneath a macaroni water pot. The heat will build up and build up and build up, and finally some of the water atoms will have enough energy to release and leave the surface of the water as steam. Let me use the phrase the maximum energy of the electrons because electrons will come out at all different energies, but let's focus on the maximum, the electrons that are coming out with the maximum energy. I'll show you how to measure that and see that in a moment. But that's what we're going to focus on. Of all the electrons coming out created by the light, let's look at the ones that have the greatest energy. Let's not look at the laggards. Let's look at the leaders. Whatever frequency of incident light, electrons will be emitted as long as the light delivers enough energy. Duh. Okay, that's for sure. That means it must be sufficiently bright. There must be a time delay. You would expect a time delay between switching on the light and how long it takes for the light energy to build up in the metal to finally begin releasing the electrons. The macaroni pot. You don't turn on the gas and all of a sudden it turns into steam immediately. It takes time. Particularly if you think about stirring the water, all the water has to come to 100 degrees centigrade before we start to get any kind of boiling, releasing of the water molecules. So we expect a time delay. The intensity of the light should increase the production of the electrons. If you increase the intensity, you should get more of a current, more free electrons coming out of this metal. The intensity of the light should increase the maximum energy of the electrons. Well, sure. I mean, if I'm pouring in more energy here with a brighter light, I should get those best electrons, those ones with the most energy, I should get them coming out at even a higher best energy. All these things are, if you think about them, are just what you would expect if there's this wave of light uniformly coming down and bathing the metal in a uniform, continuous way, building up that energy as the metal absorbs the light energy as a wave. We come to the last piece of the physics of our friend Philip Leonard. Yes, Philip Leonard was also the expert on the photoelectric effect. There was nobody who took better measurements. He was one of the great experimental physicists of his generation, no doubt about it. And you're dealing with very difficult measurements to take here. And this is about the best data he could find. He found that for different kinds of metals, here's sodium metal, here's magnesium, that as you pick up the frequency higher and higher, let's focus on the sodium, at lower frequencies you got nothing. Finally, at some frequency, which we're going to call the threshold frequency, finally you would get a very tiny current. Finally, some electrons would be released. And as you increase the frequency, the current would increase, and the current is a proxy for that maximum energy, the maximum energy of the electrons being released. He couldn't get very good data because it's very difficult, very sensitive, talking about very small quantities of everything here. He could see it vaguely went up, but he had no trend, he had no way to get any kind of mathematical law involved. But he did see that it did take a threshold energy to get the game going. And as you increased that frequency, more and more electrons were released, and their maximum energy of those electrons were getting higher and higher. That he could see. For a different metal, exactly the same kind of phenomenon, you just had to start with a higher frequency. You had to start with a shorter wavelength if you wanted to get the game going with magnesium. Magnesium seemed to have the ability to hold on to its electrons more strongly. Okay, that's a chemical property of magnesium compared to sodium. Nothing strange there, that different metals, different materials have different properties. Okay, they have different boiling points, they have different melting points, they have different spectra, they have different all kinds of things. So they have different threshold frequencies. There's nothing strange here. What's strange is that this data that he collected was independent of the brightness of the light. He needed the right frequency to get the game going, not the right brightness. He needed to wait until he finally crossed the threshold frequency before the current turned on. And the current turned on immediately. There was no time delay. As soon as you turned on this itty bitty violet light, boom, you got a current. You got electrons obviously bouncing out of this metal with a high, with a maximum energy quite high, higher than if you'd used blue light. And certainly if you use orange light, you wouldn't get anything at all. It was independent of the brightness of the light, only dependent upon the color of the light. And here are the threshold frequencies. And like I say, the increase of the intensity of the light did increase the number of electrons coming out. But as far as Leonard could see, it didn't increase the maximum energy that the electrons were coming out as. As bright as the light you could make it, the electrons releasing from the metal still had the same amount of energy, those maximum energy guys. So Leonard was able to show all of this. His theory, his explanation was, well, the energy was already in the electrons in the metal, and all the light was doing was making some kind of a catalyst reaction to make this happen. But all the energy and everything was already in the electron, just waiting for some kind of a catalyst to happen. He missed it again. He missed it again. All right. So let us just take a look. I hope I have enough bandwidth for this. I hope I don't go into a fun animation. Okay. Here we're sending out green light. We're hitting a certain metal here. Metal here is potassium. And I can adjust the voltage, and I can adjust the color, and I can adjust the brightness. Okay. And you can see with this particular color, green, and at this particular voltage, a half a volt, the electrons are being knocked out of the metal, but I am not getting anything hitting the collector plate. So in this case, I would not get any current. See, the way for me to measure the energy of the electrons is to bring the voltage down. You can think of the voltage as a wind that the electrons have to push against because it has to get to this positive plate. I'm sorry, it has to get to this negative plate, the collector plate. It doesn't want to get to the negative plate. There are negative electrons. So this voltage here is pushing against the electrons. It's literally like a wind that they have to fight against. But as I bring the voltage down and reduce the strength of the wind, finally the electrons will get to the collector plate. Okay? I haven't changed the brightness, haven't changed the color, but I finally will see a current, and this is the way I can measure those maximum energy electrons. By seeing what voltage I have to use, what wind will just stop them, that's the energy that those electrons have. And that's the way I can talk about those electrons of maximum energy. Okay, so let's bring our voltage back to where we were. And now let's bring down our light. Here is a light of a higher frequency. Can you see that the electrons are getting closer? Okay, they're doing a better job. Back to the old voltage. Okay, let's come down even further. Even a higher frequency light, oh, they're doing a much better job. Okay, against that same wind of the 0.5 voltage wind. Okay? And finally, when I bring the wavelength down into the deep violet, yeah, they have enough energy to reach the collector plate. This is how I know what energy these electrons have, by watching the at that wavelength, by watching the voltage, right? Fine-tuning the voltage. This is where these measurements come from. Okay. Just take a look for a minute and see how many electrons are coming to the collector plate, kind of on average, you know. There they are, floating in. Let's pick up the brightness now. Let's pick it up to 100. So a lot more light hitting the plate, and we're not surprised that a lot more electrons will hit the collector plate. So we're not surprised with a brighter light that we get a bigger current. We should also get more energetic electrons. This is a much, much brighter light. Watch when I pick up the voltage by one little bit. Just pick up that wind just a little bit to 0.6, and I stop them all. Every single one gets stopped in their tracks, even though I haven't touched the brightness. The brightness is not what's the factor that's creating this maximum energy. It's only the light. I was able to stop it just by picking up the voltage by 0.1. Okay. We go back to an even higher, even a more violet light. Even with that voltage, yeah, they'll get through as well. Okay, so that was the state of play. Greg, do we have any questions so far?
Peter, we have no questions.
Okay, I'm going to turn this off, guys, because you know my bandwidth is not great. So let me turn this off. All right. So who's going to explain this? This guy. This is the opening sentence of his famous paper of 1905 explaining the photoelectric effect, and it's been called the most radical sentence of 20th century physics. So let me read this to you. Notice my highlights. It seems to me that the observations associated with black body radiation, fluorescence, and the production of cathode rays by ultraviolet light, that's the photoelectric effect, and other related phenomena connected with the emission or transformation of light are more readily understood if one assumes that the energy of light is discontinuously distributed in space. It is not a wave. In accordance with the assumptions to be considered here, the energy of a light ray spread out from a point source is not continuously distributed over an increasing space. It is not a wave, but consists of a finite number of energy quanta, which are localized at points in space, which move without dividing, and which can only be produced and absorbed as complete units. Notice the finite number and the complete units here of Planck. This is a 26-year-old nobody who can't get a job in academia. He's working in the patent office, totally unknown. Even his thesis advisor has kind of given up on him. He's only working in the patent office, doing a very good job, by the way. At some point, he gets promoted from examiner third class to examiner second class. Oh, yeah, he's doing well. In his spare time, he writes 5 papers here in 1905. This is one of them, to explain the photoelectric effect. This is quite an incredible sentence, guys. I invite you to read it, again at your leisure with my red, to understand what he is saying. He is saying that light coming out this way in these productions, okay, with the photoelectric effect, with Planck's black body, these are not waves. Light is something else. Okay, what's his explanation? His explanation at base is really quite simple. He says, well, the interaction between the photon, my photon, which I'm positing, and the electrons in the middle is a unique elemental act. One photon hits one electron, if they're lucky enough, and it has an energy of Planck of 5 years ago. The energy depends upon the frequency. The energy of the photon would be h times f. And that might or might not be enough energy to give the electron to free it from the metal. We do all recognize that the electron's going to need energy to get out of the metal. The electron is kept in the metal by electrical forces and can only escape if a certain minimum amount of energy is given. Okay, that minimum amount of energy will depend upon the different metals. Sodium will hold them by one energy, magnesium will hold them by a stronger. But every metal has got a certain threshold amount of energy before you got to give the electron before it'll give it up. Thus, the frequency of the photon must be above that certain threshold value, using Planck's constant, to get enough energy to supply the energy to release the electron. That's why we have these threshold frequencies. Once we're above the threshold, the electron absorbs that photon of energy and will escape immediately with no time delay. That explains that. And if we increase the energy of the photon by increasing the frequency, by increasing the color of the light, the electrons will interact with these photons and will come off with increased energy, just as we saw in the animation, just as Leonard saw. If we increase the intensity of the light, we'll increase the number of photons and therefore the number of electrons that are escaping, but not their maximum energy, because we're not increasing the actual frequency of the light. We're just increasing the number of photons, not the energy per photon. This does explain, in words, everything that Leonard saw. But this is crazy, because you have to go with the sentence before, that light is not a wave. That light is these particles, which is crazy. Because Young showed in 1800 that light is a wave. That we have 100 years of classical physics that light is a wave. We have the whole pillar of Maxwell's electromagnetic theory that tells us that light is a wave and shows all of its properties, except for these new ones, except for black body radiation and things like the photoelectric effect. So that's where we are. So Einstein explains a little bit further. He says, it's really very simple. If you take Leonard's graphs, what he's actually looking for there, the graph he's actually going to get, prediction, Einstein is not an experimental physicist. He says, if Leonard could take better data, and I have all the respect for Leonard, but at some point when the data can be taken better, this is what you're going to get. You're going to get a threshold frequency, nothing until then. Once for sodium, you hit the threshold frequency, the maximum energy of the electrons is going to grow in a beautiful straight line. Not only is it going to be a beautiful straight line, but the slope of that line is going to be h. And if you take another metal like magnesium, yeah, you're going to have to pick up the frequency until you get to a higher frequency. But once you get that higher frequency, you're gold. Those most energetic electrons will grow perfectly linearly in the same straight line with the same slope. Really. And who are you again? This is, talk about bold prediction of a theorist. This is quite remarkable. He says, well, you know, it's very simple what I'm saying. I'm saying that the energy that you pour into the metal, Planck's formula, H times the frequency that you're pouring in, will equal the energy that you need to get to electron free, which is, there's the threshold frequency. Use up that amount of energy to free it up, and whatever's left is what will come out. We come flying out with that amount of kinetic energy. That's what gets you to the collector plate. So free it up here by using the threshold frequency, and then whatever's left is kinetic energy that gets you to the free. This is nothing more than the conservation of energy. The energy of the incoming photon is nothing more than the energy that you needed to free up the electron plus whatever is left. Come on, I'm not talking here some kind of crazy theory. I'm talking about the conservation of energy. Now, if you'll indulge me, if I could just solve for the y coordinate here, this is energy over frequency. Well, let's just go ahead and solve for the energy, right? So this is what we would write in algebra as a function. So here is the x-axis, here's the x variable f, here's the y variable e, and he says, well, look at the equation. Take the conservation of energy equation and write it in this form. This is the form y is equal to mx plus b. That should somehow or other ring with almost everybody. Y is equal to mx plus b. You've heard this a million times in 9th grade. Trust me. This is the equation of a straight line. Many of you, of course, know this very, very well. But even of you non-math types, trust me, you've heard y is equal to mx plus b a million times. It just was a million years ago. What Einstein is saying is my formula, my conservation of energy formula, is nothing more than the straight line that I'm predicting, where the slope of the line is m. Here it is, it's h. That's the slope of my line. Here is the different b's I need, the different places where the light will start. Okay. Notice, by the way, then if f is the threshold frequency, I'll get hf0 minus hf0. I will get no energy at all, which is what the graph says. That's all this is. This is just a simple 9th grade formula equation which describes what you think is such an outrageous prediction. Well, the reaction was, "Who are you again? Really? Are you kidding me?" No. It's your explanation sounds very pretty, yes, and it all would be very nice in some wonderful world of Oz, but no, this is a much more complex situation than what you described. This is not going to work out this way. We're going to need a lot more experimental data and a lot of people smarter than you. Who are you again? For this to be finally sorted out. And one of the great figures that finally did sort this out was J.R. Milliken, great American experimental physicist. He's the one who actually found the charge on the electron coming from J.J. Thomson's experiments, won a Nobel Prize for it. He made it his mission to show that this was wrong. He made it his personal mission to show that light was not in these particles, these photons of Einstein. No, this was not going to hold. Classical physics we're not going to abandon classical physics. And he made it his mission to show, by being the great experimental physicist that he was, able to use techniques, superior to Leonard's, as technology moved on, and as the genius of Milliken is greater than the genius of Leonard, he was able to take definitive data for the photoelectric effect. And this is his data. Yeah, this is his data of 1916. Here is the threshold frequency. Here is the most energetic electrons going up in a linear way with a slope of h. This data is taken by the greatest enemy of the concepts behind this data you could possibly imagine. There's your threshold frequency. He said, Einstein's photoelectric equation appears in every case to predict exactly the desired results. Yet this semi-corpuscular theory, which Einstein arrived at his equation, seems at present wholly untenable. In other words, don't believe your eyes. It's untenable. I know it's, but no, there's got to be some other explanation for this data. He later on, by the way, they basically built American physics around Milliken. They founded Caltech for him, made him the first president, and brought all those great scientists and built up the tradition, which is still Caltech. That's how it got founded, by asking Milliken to come and work at this nothing college, which they finally renamed Caltech. He says later on in life, let me see if I can read this, if I can find this. Yeah, he says later on in life, I spent 10 years of my life testing that 1905 equation of Einstein. And contrary to all my expectations, I was compelled in 1915 to assert the unambiguous verification in spite of its unreasonableness, since it seemed to violate everything we knew about the interference of light. That's basically the closest we're going to get to a concession by Milliken of this. And so this, of course, puts Einstein on the map. And this is what just these other slides for you to take a look at, a little bit of his biography, a little bit of his chronology. And here's a wonderful picture of 1911, where there he is in the company where he belongs. Okay? He is only 2 years or 3 years out of the patent office here. And he is with everybody who's everybody. Here is Curie, here is Rutherford, here is Planck, here is Lorentz, and here is Sommerfeld. Here's the greatest mathematical physicist of his generation, Poincaré. Yeah, he's with the people who finally he belongs with. And you can see the smile on his face. He's very happy where he is. So where are we in our story here? We've gone through all of this, the atomic hypothesis, going down through the understanding of atomic number. And we've gone through now the quantum hypothesis. We've looked at going down through X-rays and the electron to Rutherford's atom. We're about now to put it all together with Bohr's atom. I'd like to start this today, see if we can get through most of it. We will see Bohr's atom was a great triumph, and we'll see that it doesn't work. It is not the future. We need something else. And then next week we will start our study of quantum theory, which basically finishes up in the late 1920s. Okay, that's where we have to go. All right, well, I switch presentations. Do we have any questions?
Yes, Peter, we have one question from Leslie
Great.
Casey. Who first used the term photon?
That's a very good question. It was used quite late. I think almost like in the early 20s, I believe, photon was finally used. The word quanta was used by Planck as the quanta of energy. That's where we get that word. And I think Einstein used like quanta of light. He did not use initially the word photon, but eventually someone clever, coined that word, but I don't remember who. All right, so the Bohr atom, and this is now the Bohr. This is not the Rutherford atom. This is the Bohr atom. Rutherford never had the electrons circling around the nucleus. He knew very well that this was untenable. He knew very well that circulating electrons were accelerating electrons, just like isolating electrons, just as what Hertz did to create electromagnetic waves. As long as you get these electrons changing their velocity constantly, they will give off energy. Hertz had them going up and down, going and changing their direction very, very quickly and changing their speeds very, very quickly. Well, going in a circle or going in an ellipse is just as bad. They're changing their velocity all the time. These electrons are going to radiate away their energy and fall into the nucleus. Rutherford, of course, knew that. Everybody knew that. So yes, there was a nucleus, there was these electrons, but what to do with the electrons? What to do with these, if there were free electrons? You couldn't just have them out there moving around. You couldn't have them out there just stationary, you know, like charges attract. The electrons would just be sucked in to the nucleus if they weren't moving. It was a real problem. This is one reason why Rutherford's discovery of the nucleus was kind of a head scratcher. Yeah, his data was good, his analysis was really good. Something was up, but what do you do with the electrons? It created more questions than it solved, in a sense, to discover the nucleus, which of course happens all the time. Scientists are not surprised by this. Scientists are not at all surprised by a discovery of something new. It just shows their more deeper ignorance. That's what scientists do. Okay? That's what makes them different. They like their ignorance. They try to overcome their ignorance with new information. So we start our story back again in the late 19th century, and with the spectra of different elements giving off different colors of light. These are now emission spectra. They only give off certain colors. Is there a rhyme or reason to this? No one could see one. Okay. Here I picked off the wonderful alkaline metals, the very first column of the periodic table. All these elements have the same chemical properties. These are all the salt makers. Here are all the salts: lithium chloride, sodium chloride, potassium chloride, rubidium. These are all wonderful salts. Look at their spectrums. I dare you to find a pattern. There is none, at least none in the values of the wavelengths. But yet they all have the same chemical properties. Big question. Someone solve this? Can someone marry this? The fact that they all are salt makers, they're all in the same column, but yet their spectra doesn't seem to have any relationship to each other. Well, the prince, the god of all high school math teachers, which I was one, I taught math and physics, is this man here, Johann Balmer. He was a math teacher, high school. He's the one who found the first formula to predict these numbers. He took the simplest one of all, the hydrogen spectrum, 4 colors, 4 wavelengths, and he was like a real Pythagorean, you know, in the tradition of numbers were everything, numbers were the basis of all of reality, and he just knew these numbers they got to be something. There's got to be some kind of a sequence, some kind of formula which will predict these numbers. And amazingly, he found it. He was that kind of, God knows how he found it. He found this in his spare time. When he found this thing, it kind of made him a little bit famous. He finally got a teaching job as an adjunct in the local college. That's as high as he ever rose in the academic ranks. But he found this formula in 1885, okay, where the wavelength is equal to a constant, which he found. Here's the number, 3.64 times 10 to the minus 7. Using this, God knows how he found it, that if you use m squared times m squared minus 4, where m is 345, this is what he first used, he got the first 3 numbers. Yeah, I know, it's magic. So here it is. When you use m as 3, and you put in his formula, using this crazy number for b, you will get 6.56 times 2 nanometers. And if you put in 4 for m, and use 4 squared, if you put in 5 into m, you will get this number and this number. It was quite amazing that this line actually was not well known at the time. And finally, when this line was known, son of a gun, when you put in 6 to his formula, it worked. He found the number before the experimentalists were able to confirm exactly what the number was. This is quite amazing, but it's a piece of pure number foolery. He didn't pretend to have a theory or an idea why. But again, guys, we have discrete numbers, we have discrete wavelengths of colors, and he's bringing in discrete integers. there seems to be no way to stop this flood of units coming into physics, because it's here. It's here in the physics. It's here in the data. Here are 4 individual wavelengths. And so all these numbers do create, in his formula, as weird as it is, the proper wavelengths. A real physicist, a Swedish physicist by the name of Rydberg, he said, well, let's take a look at this formula of Bohr. Very, very good formula, very nice. Let's do a little algebra with it. Let's first of all turn it upside down. We'll turn both sides upside down, okay? And let's factor out that funny b of his, put it outside, 1 over b. And then finally, let's factor out that 2 inside there. It's a little weird. So he gets this very nice formula. He says 1 over the wavelength is a constant 4 over Balmer's b, right? Balmer found this one. So 1 over wavelength is 4 over b times 1 over 2 squared minus 1 over m squared, where m is 3, 4, 5, 6. This is very nice. This is pretty, a little bit prettier than Balmer's formula. And notice it kind of suggests a very easy generalization. What's with the 2 after all? I mean, you could put any number there, okay? You use 2, then you use 3, 4, 5. Maybe if you use 1, you can use 2, 3, 4. Maybe if you put in 3 here, you can do 4, 5, 6. It would be the same kind of form as long as I don't change this thing out here. I wonder, you know, so certainly it's going to work for 2. This is just purely mathematical manipulation. This new number here he comes up with is called the Rydberg constant. Another weird number, just as weird as Balmer's number, 1.097 times 10 to the 7th. And so he has a formula. Okay. And we know when you put in 2, it's going to create the Balmer spectrum, the places in the visible spectrum of hydrogen at the right wavelengths. We know that. He didn't do anything new here except some 9th grade algebra. But when you put in 1, you get another set of numbers. Well, Lyman, between 1906 and 1940, took a long. This is difficult because these things are all in the ultraviolet. These are invisible. Okay, it takes a while to figure out the experimentalists how to get these numbers precisely. But finally, the experimentalists did agree that you put in 1 into this formula and then use 2, 3, 4, 5, you're going to get what's called the Lyman series. The experimentalist who finally was able to definitively get the proper spectrum, color numbers for hydrogen in the higher regions of frequency. And yeah, if you use 3, you'll get the Paschen series. Okay, again, a difficult series to find. This was found in 1908 because this is all in the infrared. Okay, these colors are all invisible. You need other techniques than using just a simple glass prism to find these numbers. Okay? So it took a while for the experimentalists and physicists. So Rydberg had quite a formula here. Okay, it was really Balmer's formula, but in Rydberg's hands, he has a very powerful form of the equation which describes a lot of physics. And so the question was, well, where does this come from? Okay? Just as Planck has his beautiful formula, where the heck does that come from? Einstein has his conservation of energy formula, which is simple, but what's the ideas behind that formula? And no one had any ideas behind this. Very, very nice, attractive formula. Okay? Notice again, this is not rocket science what's going on. Okay, this here is just this Rydberg constant. And if you start with any n that you like, if you start with an n of 1, you'll get 1, right? 1 over 1. And then use 2, 3, 4, 5, and you'll get this series. If you start with n is equal to 2, start with a 4th, and then do a 9th, a 16th, a 25th, and you'll get these numbers, etc. Okay? So it's an empirical discovery, this formula, which matches the empirical discoveries of the lab. Well, this is one of the great clues that Bohr started with his atom. Okay? He's got the problem of these electrons doing something around the nucleus, but they're not falling into the nucleus. They're stable. Atoms are stable. We're here. I'm speaking. So what Bohr said was the electrons revolve around the nucleus in definite energy levels called orbits or shells. And then as long as they're in those energy levels, they won't radiate. Why? I don't know. They just don't. Literally, he had no reason why. Obviously, they don't, so they don't. Clearly, if they did, there would be no atoms, there'd be no us. So there are these energy levels which must be stable. And as long as the electrons remain in the shell, they're never going to gain or lose any energy. Interestingly, he did say that the energy levels did have to be quantized because they were discrete. Yeah. And what he did was he quantized one of the technical parameters of energy, the quantum momentum, the angular momentum. He said that the angular momentum can only come in very discrete values. In classical physics, they can have any value. What he did was he put an n being 1, 2, 3, 4. And the chunks had Planck's constant in it. So he chose this as his unit of angular momentum. So this would have an angular momentum of 1, and this would have an angular momentum of 2, and this would have an angular momentum of 3. Again, we have these integers coming into physics. I mentioned this sounds like a very technical point right now of the angular momentum, because we will come back to this when we see real quantum theory. This will not go away. This is a very interesting thing that Bohr came up with, kind of just ad hoc. And so he's got his picture of the nucleus, Rutherford's nucleus. Oh, by the way, Bohr was a student of Rutherford. Yeah, when he got his doctorate in Denmark, he got a scholarship. Where do you want to go? Oh, I want to go work with J.J. Thomson. Levi still wants to work with J.J. Thomson, Cavendish. He spends a couple of months with J.J. Thomson. They do not get along. They just do not get. J.J. Thomson, he has no time for this young man. He's very, very busy. He doesn't speak English all that well. J.J. Thomson's getting on in years. They just don't get along very well. He sheepishly says to Thomson, "Do you think it would be okay if I went up to Manchester to work with your student Rutherford?" He says, "Yeah, that's a good idea. Go bother Rutherford." And he goes up to Manchester and is welcomed by Rutherford. He sees he's a pure theorist. He puts him in. He gives him a lab bench, suggests something to do, which he knows he's going to ignore anyway, because he's really not much of an experimentalist. Never was. That wasn't his interest. He's working most at his desk in his room up there in Manchester. And Rutherford says, "Okay, that's fine. Well, you come up with something." So he comes up with this. And he comes up with these different energy levels, these energy shells, which I'm naming here as E1 to E4. They all have a various energy value, depending upon this quantized angular momentum. And he says, what's going on here, how light is being created by these atoms, is if when an electron goes from one high shell down to a low shell, since we know what the energy of the high shell and the low shell are, it gives off the difference in the energy. Duh. It goes from an energy of, literally using the numbers for simplicity, an energy of 6 down to an energy of 2. It'll give an energy of 4. Again, I'm using just the simplest concept, because the energy actually is given off as quanta of h times the loss of frequency. Whatever frequency is given off by this decrease of energy is, h times f will be this change of energy. So again, h appears here as the building blocks of energy. Okay? So this energy level represents some amount of energy in h's. This represents some amount of stable energy in h's. And when you drop from one to another, you'll give off a bunch of h's in a certain frequency. That's the light that's being given off. The same thing goes the other way. If you can give an electron energy, like the photoelectric effect, like heat, like anything, you may bounce up an electron from a lower energy level to a higher one, like going from, for example, 1 to 4. And then in that case, you would want to calculate how much energy it needs to get up there. I'm sorry, this is a 2. I'm sorry, this should be a 1. Going from 4 minus 1 That's how much energy, it's exactly how much energy you need to get up to that fourth energy level. Again, another multiple of some HF. So you can pick any F you like. There's just, whatever light you want to shine on this thing, but you can only use, right, discrete blocks of it, units of H. Okay. So this is his idea. This is how he incorporates Planck's idea of the quanta of energy. And everything will be stable as long as you stay in these shells. And if you want to move from one shell down to the other, you will give off quanta of energy in units of HF, proper F. Or if you want to pick up, for example, the photoelectric effect, if you want to take this thing and send it all the way out, then you better find the right threshold energy, the right one, so that when the electron absorbs it, it can be freed up and go on its merry way if there's some wind that'll blow it, etc., volts and whatever. So this is his idea. It's an idea, okay? It's a crazy idea. It's completely against all of classical physics. It's a brand new idea. And again, you can only get these jumps by discrete amounts of Planck chunks of energy. Well, he's able to produce the spectra of hydrogen. He's able to produce the Lyman, the Balmer, and the Paschen series. He says, what's the original Balmer series? It's really very simple. It's when you go from the, where are we? 1, 2, 3. When you go from the fifth energy level down to the second, you'll get that beautiful violet light. When you go from the fifth down to the second, you'll get the green light. And when you go from the fourth down to the second and the third down to the second, little bit of energy, you'll get those orange and red lights. When you drop down all the way from the sixth down to the third, this is not such a big drop. Here you'll get the infrared. You'll get exactly the infrared numbers of Rydberg. And when you drop down all the way down to the first level, you will get very, very high energy drops. You will get the ultraviolet drops. And by doing the energy levels right, by keeping an eye on these series, he knows what numbers he needs. He knows what kind of energy levels he needs. Oh, well, any competent mathematician can cook up, Rydberg's formula using the right energy levels. This is cheating. This is like, back in high school chemistry when you read the lab and you made up the numbers to fit the lab so the teacher would be happy because you know that your numbers you measured never worked out. This was pretty easy to do because he had all the numbers in front of them and he had the Rydberg formula to fit. Yeah, but one thing, not only did he derive the Rydberg formula, he derived theoretically what the Rydberg formula should be. And it should be the mass of the electron times the charge of the electron to the fourth over 8 times the permittivity of electrostatic charge squared times Planck's constant cubed. And that is that's some kind of a nightmare. He derived that mathematically through his assumptions based upon the quantization of angular momentum. See, guys, he had the energy levels, and therefore he was able to calculate the distances and the speeds of the electrons going through these orbits. Well, once he had this and the speeds, he had the kinetic energy and the potential energies. Then he had the sum of the energies, and then he could calculate what the drops in energies should be. But the energies coming from the kinetic energies and the potential energies, he really needed the radiuses and the velocities, and he got those from the charge on the electrons and the charge on the nucleus and the electrostatic force, the Coulomb force. He used these classical formulas to derive the Rydberg formula, and in the process he derived the Rydberg constant. This is very, very impressive. This is not working backwards, okay? This is deriving this crazy, beautiful looking expression, which is the Rydberg number. Okay? So this is the Bohr atom. This is quite a triumph to predict the hydrogen, sorry, the hydrogen spectrum. Okay, so we will stop here. You can open up the mic. Are there any questions on the chat box, Craig? Or
Peter, we've got a comment and a question. So Joe
okay.
Parisi found Gilbert Lewis first coined the term photon in
Thank
late
you.
1926.
That's right. The great chemist, yes.
And Joe Parisi asks, are there equivalents to the Balmer and Rydberg constants for elements other than hydrogen?
Well, that's going to be our story. This atom, as wonderful as hydrogen, does not work for anything else, not in this kind of level of detail. Some of the vague ideas of the energy shells will keep, but to calculate, if you want to calculate the spectra of the more complicated elements, even starting with helium, you need quantum mechanics. You're not going to get these simple formulas like Rydberg. Those days are going to be over. We're going to need Schrodinger's equation. We're actually going to need Dirac's electron equation. So no, this is the last of the simple classical equations. Okay, if you want to open up your mic, any other questions, any other comments?
Yes, Peter, I have a question about, can you hear me?
Yes, I can.
Okay, thank you. I have a question about the formula in this particular slide, Bohr atomic theory, 1913. Would you say again what the term, it's the E squared, would you say what that is again, please?
E squared is a constant of nature that you measure in the lab, which are all predicted also in electromagnetic theory. You find itself when you want to compute the electrostatic force between a positive and a negative charge. It's called the Coulomb force.
Okay.
You need this constant in order to calculate that force, just the way you need the constant capital G with the masses of the two planets to calculate the gravitational force. That's where this constant comes from. It's called the permittivity of free space.
Okay, and I have one more quick question. In your third from the last, or the two slides up.
This guy?
Nope, one more down, sorry.
This guy.
Yes, thank you. When electrons are moving to a higher energy level, does intensity, if the intensity of the light at that particular frequency is increased, does that cause that movement to occur more rapidly?
Okay, you've hit upon another sore point of the Bohr atom. The Bohr atom cannot predict the brightnesses of the spectral lines.
Okay.
They could only predict the frequencies or the wavelengths. He was not able to predict very well the brightnesses. So the whole question of brightness was still an unknown. That's going to have to wait for the Schrodinger equation. Very good question.
Thank you.
Okay. Any other questions before we go? All right, then I'm going to stop the recording and we'll see you guys next time. We will start quantum mechanics next time. Have a good week, everybody.